All right, welcome back. So here we continue with the design procedure for the flexible coupling. So we have seen in the previous lecture that flexible coupling constitutes the design of flanges, the left flange and the right flange, and the left flange carries a push pin type of larger diameter. Uh, So we need to design the flanges, we need to design the bush, we need to design the pins, and then we need to design the keys. So there are various parameters in the design of flexible coupling. So here also we give a quick review what are the parameters we need to design. So first of all, let us talk about shaft diameter. So let us say that it is given that um, the shaft is required to transmit torque mt at an rpm n, so we can always determine what is the diameter according to the shear strength criteria, right? So in the dimensions of the flange we have the dimensions like dh, diameter, length of hub, diameter of hub, capital D, which is pitch circle diameter of the extreme holes through which the pins have to be inserted. This T is the thickness of the flange, and T1 is the thickness of the protective ring. Right, so these are given to be TH as 2D, 1.5D, 3D to 4D. Thickness of the flange is 0.5D, and thickness of the protective ring is 0.25D. So once we calculate the dimension of the flanges, we check with the uh, we check with the whether the design of hub is safe or not, because the hub is nothing but it is considered as a hollow shaft, right? So we calculate the shear stress of the hollow shaft when it is subjected to torsional moment mt. So on those basis we can decide whether dh and d are safer to design or not. So I think the same relations we use here, tau is equal to mtr by j, which is coming from torsion equation, where j is polar moment of inertia. Since the hub is now a hollow shaft, it is pi by 32 dh to the power 4 minus d to the power 4, because internal diameter is nothing but the diameter of the shaft. R is diameter of the hub divided by 2. So same way we can calculate the shear stress in the flange at the junction with the hub can be calculated as mt is equal to half pi dh square t tau. Further we have apart from these basic dimension of the flanges, we have the pins and we have the bush. So for pins, since we have this empirical relation d1 is equal to 0.5d divided by root of n, so where n is the number of pins, generally we have a 4 to 6 pins, so we can calculate the diameter of pin as d1. And also this diameter we must ensure that it is not failing under the shear stress criteria. So tau is equal to, we have previously derived this in the previous lecture, tau is equal to 8 mt by pi d1 square dn, right? And this shear stress for pins is limited to 35 megapascal. Okay, so from this criteria we can see whether the design d1 is safe or not, it is within the permissible limit or not. You can also design for check for the diameter d1 for the bending stress calculations. So it is very important that once you evaluate d1 from this equation, d1 is equal to 0.5 d by root n, you evaluate from shear stress point of view as well as from bending strength point of view, that this d1 is safe to consider. For the dimension of the bushes, we need to calculate the outer diameter of the rubber bush. We can use this equation, mt is equal to half db square dn. We have seen the derivation of a quick derivation of these equations in our previous lecture. So further we can calculate, we have assumed in these equations we have assumed that length of the bush is equal to diameter of the bush. So length of bush can be computed as lb is equal to db. Further we have the keys. The length of the key is nothing but length of the hub, which we have already evaluated. So once we have taken the standard, depending upon the diameter, depending upon the diameter of shaft, we can choose the cross section of the key for, and this is specifically for sunk keys, maybe square or rectangular, and the keys are also subjected to 2 points of view. One is tau, shear stress, other is sigma c, that is compressive stress. And we have obtained these relations: tau is equal to 2mt by dbl and sigma c is equal to 4mt by dhl, particularly in the chapter of design of keys. So we have derived these expressions as well. Now we get these dimensions of the key from these equations, from the shear strength criteria as well as compressive strength criteria, right? So by this, now we can see that we, for the design process of flexible coupling, we need to design for the flanges. We need to provide the geometric dimensions of pins and bushes. We need to provide the geometric dimensions and as well as cross section for the keys. So there are 4 or 5 parameters in the design procedure of flexible coupling. Let us move forward towards certain illustrative examples. Let us say you have a flexible coupling and it is required to transmit 15 kilowatt power at 100 rpm. So at first instance, I get is rpm is known to me, power is known to me. That means I can always get the torque transmitted. That, right? So power is equal to 2 pi nt by 60. There are 6 pins. That means n is capital N is equal to 6 and their pitch circle diameter is 200 mm. So it is already given, it is not an output parameter now, it is already given that what is the pitch circle diameter, 200 mm. The effective length of bush LB, the gap between two flanges and the length of pin in contact with right hand flange are 35 mm, 5 mm and 23 mm respectively. I think there is a one point which I'll put here. The second criteria which is given, the gap between two flanges. In general, the gap between two flanges is 5 mm for pin type, bush pin type flexible coupling. The gap between two flanges, that is left flange and right flange, there is certain gap and that is 5 mm. Though it is given in this problem. The permissible shear and bending stress for the pin are 35 and 152 megapascal. Newton per mm square is nothing but megapascal. Calculate pin diameter by shear consideration, pin diameter by bending consideration. So in this particular problem, it is not being asked to design all the parameters of the coupling. Only thing they have focused on how to design the pin. Okay, the bush dimensions are not known to us, pitch circle diameter is known to us, as well as length of the pin is also known to us, right? Shear and bending stress for the criteria is also known, that is 35 megapascal and 152 megapascal. So let us see how we proceed. We know that pin diameter by shear consideration. First of all, we try to get what is the torque transmitted. So torque transmitted will be 60 kilowatt divided by 2 pi n. So you take care of the units and get torque transmitted as 1432394 Newton mm. So further what we have is according to shear stress consideration, tau is equal to 8 mt by pi d1 square dn, where d1 is the diameter of the pin which we have to evaluate. Tau is the permissible limit which is given to us as 35 megapascal. Mt we have already evaluated. Capital D is also known to me now. It is given 200 mm. Capital D is pitch circle diameter. Pi is a constant. And capital N is number of pins, which is also known to me, that is 6. So that means we simply get what is D1, what is diameter 1. And it comes out to be 9.32 mm. Let us say 10 mm. Now this is pin diameter by shear consideration. What will happen when we talk about the bending consideration? Please have a look at diagram very carefully. This is a pin cross section. Okay, and this is a bush will apply a uniform pressure. Okay, and there will be a force acting on each bush, and there will be a torque mt, right? These forces and torque can be interrelated by mt is equal to p into d by 2 into n. Okay, we have already seen this expression if you recall in the design of pins. So we get p is equal to 2mt by dn. So it means now we can get what is the force which is acting on this bush, right? This p is known to me, that is about 2.38 kilonewton. Now this p is, it is a reasonable assumption that p is acting distributed uniformly over the bush length, which is given to be as 35 mm. So these are the dimensions which are given to me. The bush length is 35, the gap 5 mm, and then we have this right flange. Okay, this is the left flange, this is the left flange, and this portion is the right flange. Okay, so these are the gaps. So you can see the dimensions, we can go back and check. So the effective length of the bush is 35, the gap between the two flanges are 5, the length of pin in contact with the right hand flange is 23. So we can see in this diagram 35, 5 and 23. So at this end, at the top end in this diagram, there is a left flange. At this end there is a right flange. Obviously it is clear as well from the washer and nut. Okay, so once you do that, I think now you can take out do the calculation to see what is the bending moment acting at this point. So the bending moment acting is P into 5 plus 35 by 2, because at this point, okay, so at this point the distance is, this is 5 mm, and 35 by 2 you can always assume that it is acting through at, because it is a uniformly distributed, so acting through its center. So your bending moment is 23p into this distance, that is 22.5. So you get the bending moment. So once you get the bending moment, you can apply for bending moment equation. Sigma b is equal to 32 mb by pi d1 cube. The only unknown here will be d1, because mb we have already evaluated. Sigma b is also given to me as 152 newton per mm square. So since it is consistent with units, so we need not play with changing of the units. So the only unknown is diameter. So d1 comes out to be 15.33 millimeter. So if you see the previous calculations, by shear consideration the d1 is 10 mm. By bending consideration the pin diameter is 16 mm. So that means we need to take the diameter of the pin is at least 16 mm. At least 16 mm, right? So it is very important to see both the design, both the criterias. Sometimes it may be feasible that we go with only shear and we ignore bending, but we do see here that the bending is significant, because the load is, since the torque is very high, the amount of force is also very high. Okay, so it means it will produce a lot of bending, right? Otherwise what we have to do is, in any sense, if we can increase the length of the bush, okay, then we can assume that slight less amount of bending will occur, right? All right, so same now, in this particular problem I think we had only the design of the pin. Let us now go to a problem where we have to design the whole coupling. So it is required to design a bushed pin type flexible coupling to connect the output shaft of an electric motor to the shaft of a centrifugal pump. Okay, so we have an input as electric motor, and we have to connect it to a centrifugal pump. The motor delivers 20 kilowatt power at 720 rpm. The starting torque of the motor can be assumed to be 150% of the rated torque. Okay, so that is generally, I think, we know that the starting torque is more than the rated torque, so that is given to be 1.5 times of the rated torque. Now you can see there are not much data is given to you. Now you have to design the coupling on your own and specify the dimension of its components. It means you have to design what are the diameter of the shaft. Starting from the diameter of the shaft, you have to design the pin, you have to design the bush, you have to design the hub, you have to design the flanges, and you have to design the key. Okay, so these are few parameters which you look at. So first of all, let us say see what is the diameter of the shaft. So since the design torque power required is 20 kilowatt and rpm is 20, and design torque is 1.5 times the rated torque, that means we, okay, I think the first part we should do is we should select certain materials. Okay, because we have shaft, we have flanges, then we have pin and keys. So shaft is generally a ductile material. Shaft is generally made up of ductile material. Let us say that we are dealing with plain carbon steel of 40C8. You can definitely go with any other material, but I think it must be a ductile material as far as applications are considered. Okay, so plain carbon steel with the 40C8 having a tensile strength of 380 megapascal is used for the shaft, and let us assume the factor of safety as 2. Also, the keys are subjected to shear and compressive strength. The keys are also considered to be made up, assumed to be made up of ductile material. Let us say we use the 30C8 material with tensile strength of 400 megapascal. Again, the factor of safety for key as well as pin is taken as 2. Okay. Also, we assume that compressive yield strength is 150% of tensile yield strength. That is one assumption which we take, because we are designing on the base of compression for particularly for the pins. Okay, so let us assume that the compressive yield strength is 1.5 times the tensile yield strength. So these are few assumptions which we are taking up in our design. Then we have the flanges. Flanges are generally made up of a brittle material like grey cast iron. Okay, so FG200, which means that its ultimate strength is 200 megapascal, that is selected. And for flanges, we generally take higher factor of safety. So here we are assuming factor of safety as 6. Okay, so for shaft, we are choosing 40C8 material. For key, we are choosing 30CH. And for flanges, we are choosing FG200. It is very, very important to have a good choice of materials, particularly in open book scenario. And we must be very well aware that which materials are of the selected materials are of which type. For example, the flanges are generally made up of brittle materials. Keys, pins, shafts, they are made up of uh, ductile material. We need not go with the choice of bush, because that is a rubber kind of material as far as mechanical design is concerned. Now let us go with permissible stresses of these, because we are taking up the factor of safety for each. First of all, shaft. For shaft, we require the shear strength. Okay, shear strength is 50% of the tensile strength that you can put a basis of due to the von Mises theory, divided by factor of safety. That means the allowable shear stress is, if you do the calculation, that is comes out to be 95 megapascal. Okay, same way for the keys. Keys will also be subjected to shear stress. So SSY by FS, again it is 50% of the tensile strength. The tensile strength of 30C8 is 400 megapascal, which will come out to be, after using a factor of safety of 2, the shear stress strength of a key is 100 megapascal. For key, we will also require the compressive strength. Okay, for compressive strength, if we see our assumptions, we assume that the compressive strength is 150% of the tensile strength. So sigma yc is 1.5 syt divided by factor of safety. Again, we are using the same factor of safety for the key. So that is 300 megapascal, right? So same way for pin. Pin, we have general guidelines that the shear strength should not exceed 35 megapascal. Okay, so that we are uh, following the Indian Standard Code 2693 revised in 1980. Okay, then we have the flanges. Okay, for spin may be subjected to direct tensile stresses. So there, that ultimate tensile strength will be, sorry, not ultimate, allowable will be tensile strength divided by factor of safety, that is 200 megapascal. Okay, and at last we have the flanges. For flanges, if they are subjected to shear, as SU, here we are using the ultimate because it is made up of a brittle. In all other materials, we are choosing the yield. Okay, so this is 50% of SUT divided by factor of safety. And one more thing, here we are choosing the factor of safety as 6. So 50% of 200 divided by 6, that means just 16 megapascal. So you can see that the flanges are designed with a higher factor of safety. Okay, now let us come back to the problem. So how do we go into the diameter of the shaft? Since we are known with the power, we know the RPM. So we obviously know the relation that power is equal to 2 by n times torque divided by 60 or 60,000. So we can always get what is the torque, and this will be nothing but the rated torque. So but we need the starting torque, that is the maximum torque should be 1.5 times of this. So this 1.5 time is coming from that. Okay, so mt is coming out to be 397,887.36 newton mm. So once you get that, your tau is equal to, we have this equation, tau is equal to 16 mt by pi d cube. We have already seen that tau is 95 for the material 40C8, which we have chosen for shaft. That means we decide the diameter as 27.73. Please keep in mind 27.73 is not 28, but 27.73, you have to go to the design tables for the shafts. The shafts are manufactured for a standard diameter. So 28 diameter, 28 mm shaft is not available. So we go with a shaft which is manufactured for 30 mm. All of our further design is based on d is equal to 30 mm, right? So next, the dimension of the flange, which we know clearly, that dh is the diameter of the hub, which is taken as 2d. So length of the hub, capital D, which is pitch circle diameter, it is up to us 3d to 4d. Let us say we are going with capital D is 4 times of diameter of the shaft. So 120 mm. T is the thickness of the flange. T1 is the thickness of the protective rim. So we got these dimensions as we see here. Now we have to ensure whether these dimensions are right or not. The hub is treated as a hollow cylinder subjected to torsional movement, right? So outer diameter of the hub is nothing but dh, and the inner diameter of the hub is nothing but the diameter of the shaft, which is 30 mm. That means the outer diameter is 60 mm and inner diameter of the hub is 30 mm, and hub is also subjected to the shear stresses. So we can go with the polar moment of inertia, that is pi by 32, 60 to the power 4 minus 30 to the power 4, and we can employ the torsional equation. Tau is equal to mtr by j, and tau is coming out to be 10 megapascal. That means just 10 megapascal stress is being produced. But what is the limit for the hub material? It should be less than 16.67. If you go back and see what are the here, the shear stress for the flange is 16 megapascal, but the actual is 10 megapascal, obviously after using a factor of safety of 6. So that means our design is safe. for the flanges. So let us say we will stick with this. If it is not the case, what we do is we increase the diameter. We increase the diameter, DH, because we can take it from 2D to 3D. Okay. Further, let us say the shear stress in the flange at the junction of the hub. This is also given by 4.2 mt by pi dh squared t. It will come out to be 4.69 megapascal, which is also less than 16.67, and hence the stresses are within the permissible limits always for the flanges. Further, let us see what are the diameter of the pins. So the number of pins are, let us say we have to decide the number of pins on our own. We can go with 4, 6, 8. Let us say we choose n is equal to 6. So according to the empirical relation, small d1 diameter of the pin is 0.5 d by root n, which comes out to be 7 mm. Okay. Now this 7 mm we cannot choose directly. We need to ensure, as in our previous problem, we need to ensure that this 7 mm diameter pin is safe as far as shear strength is concerned, as well as the bending strength criteria is concerned. So shear stress in the pin is calculated by tau is equal to 8 mt by pi d1 square dn, which is coming out to be 28.72 megapascal, and the permissible limit, if you recall, it is 35 megapascal. So that means it is safe on the basis of shear strength. However, we have to also decide the bending strength. But like if we see in the previous problem, for bending strength in the pin, we require what is the length of the bush. Okay, so therefore let us first do the dimension of bushes, and then we will go with uh, design of pin on the basis of bending strength. Okay, so dimension of bush, let us say that dB, we have a simple equation, dB square is equal to 2 mt by dn. So dB will come out to be 35 mm, and we always go with the assumption that lb is equal to dB, length of the bush is equal to diameter of the bush. So that means it is 35 mm. Now we will go back to the bending stress in the pins. So again the same relations, for we can always convert the torque into the equivalent force. So we have to evaluate P first in order to evaluate the bending stresses. So again the same problem, like this is the force P which is trying to produce the torque mt. So we can get the magnitude of force P, and again we are assuming that the gap between the left flange and right flange is 5 mm. This 35 mm we have already evaluated, this is nothing but length of the bush. We do not require this dimension for calculation of the bending strength. So the maximum bending moment, the MB, will come out to be P times 5 plus 35 by 2. That is, it will come out to be 1105.25 is nothing but force into 22.5 is nothing but distance. So we get the MB, bending moment. Now the bending stress sigma b is equal to 32 MB by pi d cube. We have already seen what is the bending strength for the pin. Pin is made up of 40 Ce8 material having a tensile strength of 400 megapascal. Since we are using the right, it is a pin, so sigma b is 200 megapascal. I think we have done the calculation at the beginning. Let us have a look at back. Okay, is this pin bending strength, tensile strength or bending strength, it is 200 megapascal. So we are going to choose this 200 megapascal. So once we do that, we the only unknown here is d1. So once d1 is out to be 10.82 or 12 mm, because again the diameter of pin is available in the standard sizes. So it is 12 mm. Now, I think we can see what various types that in the initial stages the diameter of pin was calculated as 7 mm by using the empirical relations. So if we go back, this is 7 mm. Okay, by shear strength criteria it is safe, but as far as bending strength criteria is concerned, it requires a pin of 12 mm. So we need to take it as 12 mm pin. We cannot go with 7 mm pin, right? So because it will fail because of the bending. So hence the bending becomes the criteria of design for the pin. So again, you can see there are various things in design. So let us say uh, this is a pin here. What happens is the diameter of the pin should be enlarged at the section XX in order to fix the pin in the driven flange. So let us say the enlarged diameter is 6 mm. So 12 plus 6 is 18 mm, right? So what are the dimensions of the bushes? Pin and the bush are shown. The thickness of the brass lining, because there is a brass lining here, this is a pin, the pin has to be inserted through this. The brass lining is this, you can see in between the bush and pin, it is of 2 mm. So therefore inner diameter of the rubber bush is 18 plus 2 plus 2, 24, 22 mm. This is the inner diameter of the bush, and the minimum thickness of the rubber bush is usually 10 mm. Okay, so therefore the outside diameter of the rubber bush is 42 mm. So you can see from the diameters of the pins we can get the diameters of the bushes. That inner diameter is 22 mm after considering the enlarged diameter as well as the thickness of the brass lining. Okay, and outside diameter is 42 mm. Now let us go into the design of the key. So these are the dimensions which we have written for. You can see pitch circle diameter, ECD, other dimensions you can show in sketch itself. So the last part which we have to see is the dimension of the keys. Let us say we are going with a flat sunk key. Okay, since the shaft diameter is 30 mm, we can go back to the table and we choose that the thick cross section is 8 cross 7 mm. Okay, and the length of the key L is equal to LH, generally the length of the hub, which we have already decided, that is 45 mm. That means the dimensions of the flat key are 8 cross 7 cross 45 mm. We can go away with this dimension, but we need to first ensure whether the key is safe as far as shear strength as well as compressive strength is considered. Okay, so from shear strength we get tau is equal to 2mt by dhl, which is coming out to be 168.42 megapascal. Okay, and I think we have miscalculations here in this table. So tau is something else. Sigma c is 2mt by dhl. Okay, we have the same equations here. So sigma c is 168.42, which is coming out to be less than 300 megapascal, and this also will come less than 100. Okay, so that means we need to check the calculations at this stage. So that means shear and compressive stress induced in the key are within the permissible limits, and hence the design is safe. So with this, I think we can carry out the design of the bush pin type flexible coupling, uh, which involves the design of shaft, particularly the diameter of the shaft, which involves the design of hub as well as the flange, which involves the diameter of the hub, length of the hub, then pitch circle diameter, then thickness of the flange, and then thickness of the protective ring. Okay, and then further we went for design of pins, which we choose the diameter, and then we will check according to shear strength as well as the bending strength. Then we will also determine the dimension of the bush. At last we determine the dimension of the keys. So these are basic steps which we must follow as far as the design of flexible coupling is concerned. Thank you.